Okay, yeah, thanks for having me here. And yeah, it's my first time, let's say, speaking in this building. Okay, but yeah, it's a very nice environment. So I'm going to tell you a little bit about basically, in general, how sequential deep related variable models work. Basically, the motivation for here is you want to deal with sequence data, and in particular, my lab, we do quite a lot of things on sequence modeling, including things like videos. Okay, so these days, basically the current battleground for generative AI is basically video generation. So they have very advanced techniques, but we are not going to talk about that. Instead, we're going to start from basics, okay, and let you understand a little bit about how we can do deep generative modeling for sequences. Okay, well, the first thing is just demonstrate to you how ubiquitous the sequence data you have, right? Well, apart from the video data that we are interested in, right? So speech can definitely be viewed as a sequence. Well, at least it's a sequence of audio signals, right? So if you have text, although I don't personally think that text is a purely sequence, but you can still view a sentence of words as a sequence, right? Similarly, you have, let's say, this physics simulation, giving you a simulation sequence. You also have healthcare data, let's say, patients monitored in these intensive care units that you definitely have this healthcare data. And the financial data is obviously also a time series data. So, well, traditionally speaking, there are also other structures that can describe text. For example, people also talk about as a parsing the text into say tree structure and other structures. So in that sense, I don't view the text as pure sequence data. I will tell you later how I view about this. Okay. So so you have different kind of sequence data, but what we are interested in, at least in my lab, okay, is basically the kind of sequence data that actually has the underlying governing dynamics there. So this also comes back to the previous question you asked, right? That you might actually wonder whether there is an underlying dynamic system, okay, within this say, text generation procedure. Okay, so that is a question mark, but at least if you think about things like physics simulation, there is an underlying dynamic system, right? And for other kind of data like this climate data or geographic data, people also use, let's say, dynamic system to model it. Okay, so for this kind of data, we assume there is an underlying ground truth dynamic system, but we don't observe that, right? So we only observe the data coming from this simulation process. So the interesting thing that we want to do here with deep learning is can you actually just take this data in raw form, right, as input to your neural network and let your neural network be able to learn these representations such that it presents the underlying dynamic behavior. Okay, so this is the question that my group is interested in solving, okay, with various different kind of techniques. So again, let me give you a rough view about the available sequence generative model at this moment. We are not going to talk about all of them because there are way too many. We don't have time, right? But roughly speaking, if you're talking about modeling dynamics, right? So you can roughly categorize these things into this quadrant thing, right? With two different orthogonal dimensions. So either you have say the underlying dynamics is deterministic dynamics or stochastic. We'll talk about difference later. Or the model itself is a discrete time model or continuous time model. Okay, so yeah, for example, let's say the difference between discrete time and continuous time is basically whether you assume, let's say, the underlying model, you need a continuous time model. If you're going to do continuous time model, then you're going to work with, let's say, ODE and PDE or say a stochastic differential equation if you're going to assume a stochastic dynamics. In discrete time, though, that is usually what people do with, recurrent neural networks. Okay, then because you use recurrent neural networks, that is a discrete time iteration, then your underlying assumption for your model is also discrete time. And definitely within discrete time, you can also talk about whether the underlying dynamics is deterministic or stochastic. Okay. I mean, so there are definitely other kind of models not strictly speaking within this classification, right? So there are these temporal point processes. Okay, that is something very interesting, and obviously also these autoregressive models. That one of the very representative models right now is basically transformers that models the sequence generation in a autoregressive way. Okay, but as I said, we are mostly interested in recovering the underlying dynamics, which assume is not like autoregressive. We are more interested in really trying to see whether we can put some dynamic model in the latent space and then try to recover it from data. Okay, so basically this is what I'm going to talk about today. Okay, so I'm not exactly sure whether all of you actually know latent variable models. I'm going to actually start from latent variable models in static data. Okay, which means we are not going into this time series yet. Okay, and then once we set the ground of latent variable models, and then we will talk about how to extend basically, let's say, latent variable models for image generation to latent variable models for sequences. Okay, so there are some similarities and also there are some differences. Cool. Okay. So the first thing to talk about here is basically deep latent variable models, and I'm going to use this example of generating cat images as an example. Okay. So essentially, we basically said that to model the distribution of an image, right? You need to first understand the behavior of the image. So for natural images, right, they are sort of like supported in a low dimensional manifold in the full pixel space, because not every say possible image with, let's say, random pixels are valid natural images, which means the underlying dimension of this natural image manifold is actually low dimensional, so that you can assume, okay, I can put in a low dimensional variable Z, okay, to a neural network, so that this neural network can help transform this low dimensional noise Z to a natural image, let's say a cat. Okay, so this is the assumption we have in terms of the generative model for the cat. So technically speaking, in the latent variable model language, this says I'm going to have this kind of latent variable model where I have a latent variable Z that is unobserved, so that the name is called latent. Okay, and then my observation X is generated conditioned on my latent variable. Okay, so that you can think about this model, to give you a model distribution of your data, and then you can actually fit this model to the data, right? That will help you optimize this parameter. So in particular, to calculate the probability of, let's say, this cat under your model, right? Which means you need to calculate P of X. It means you need to basically compute this integration. Okay, you need to compute the integration over that. Okay, this basically says, okay, for every possible Z, I need to evaluate the corresponding likelihood term, which, remember, from our definition here, okay, requires you to pass that latent variable through that neural network, and you need to do that for every possible latent variable Z, okay. So this is not very efficient, okay, and in fact intractable. Okay, so let me talk about why you're actually interested in computing this marginal distribution. So I mean, you need to fit your model to the data, right? So then what is a good objective to train your model? Okay, so in statistics, right, there is this very classical technique called maximum likelihood estimation, which basically says, okay, the way I'm going to train my model is by maximizing, let's say, the likelihood of my model to explain my data set, which means you want to maximize your log px, okay, under the expectation of your data set. Okay, so you can see here, you do need to compute this integral, right? But as we said before, it involves a neural network, so you cannot do it Okay, so this basically, as you cannot directly do, you need to find some way to approximate this. Okay. So then here comes the idea of variational autoencoders. Okay. So remember previously we said that the maximum likelihood objective that we want to maximize is intractable, but if we can find a lower bound of that objective, then our hope is that if we can push that lower bound up, then hopefully the actual objective we want to optimize can also be pushed up. Okay, so this is the idea of variation inference, and when you apply this thing, it is called variation autoencoder. So let me explain a little bit. Okay, so we start from the maximum likelihood objective, which is basically the log of the marginal likelihood we want. Okay, so we clearly know this is intractable. Okay, the first step to do this is I'm going to rewrite this thing a little bit. I've just within the integral term, multiply and divide the same term. Thank you. Okay, so this does not change anything yet. The second step is basically to apply Yingzhen's inequality. Okay, to notice that log is a concave function. The idea to see this is actually very simple. I'm not sure whether you can see this. If you have a concave function that looks like this, right, then essentially it tells you that basically, right, so you take the two inputs and then take it the mean, and then basically it tells you that basically the mean of the function here, right, is smaller than the function evaluated at the mean. So this is essentially why we can get this inequality here. So that's the idea from Yingzhen inequality. Okay. So if you accept that, then this one is actually easier to compute. Okay. So here's the thing we can do, right? So we just play around with the terms and move around, right? And then also exploit the fact that log of product equals to sum of logs, right? Then this will basically help you to break down these two terms into, let's say, the first term that is usually called data likelihood term, or sometimes called negative of reconstruction error. And the KL term there is also something that later on we can compute. Okay, so my claim here is basically by using this Yingzhen's inequality, right, we have constructed a lower bound to the actual objective we want to optimize. So that basically means our hope, as I said, is if we can optimize the lower bound, then hopefully the actual objective we want to optimize can get increased, although there's no guarantee. Okay, but in practice, usually this happens. Okay. Yes. So I'm going to talk about how you actually construct Q. Okay, and later on for this sequence part, there are also a lot of choices for Q. Okay, so yeah, I guess another thing to talk about here is why there is this name of autoencoders, right? So the autoencoders definitely include a encoder and a decoder. Roughly speaking, you can view this P of X given Z as the decoder part and Q of Z given X as the encoder. So that's where the name autoencoders come from. And the name variational comes from our construction of its objective. So this is actually variational inference in the Bayesian modeling literature. Okay, so now let's have a look in terms of how we can do this, right? So let's get back to our model, right? So first, the good thing here is, okay, our likelihood P of X given Z is assumed to be Gaussian, okay? Then if you just plug in the definition of Gaussian density, right, then the first term is actually quite intuitive, right? So the first term here will result in a negation of the L2 error or the reconstruction error. So it really tells you, okay, maximizing the first term here basically asks you to minimize the reconstruction error. Okay, so this also again reflect this autoencoding part because autoencoders are trained to minimize reconstruction error. Okay, so I hope we are now happy with the first term, but then there are some other terms, right? This KL term, how do we actually do it? Well, there's quite some other common choices of Q. At least one very common choice here is to just again use Gaussian distribution. Okay, we really love Gaussians. So in particular, you can think about parameterizing a Gaussian distribution for the Q with both the mean and the variance coming from a neural network. Okay, what does that mean? So yeah, essentially you can basically say I have a neural network, maybe with different heads, right? That may have slightly different parameters. One of the heads will output the mean, and another part of the network will basically output the log of the standard deviation. I mean, that's one way of doing it. The reason to do this is you need to ensure that the standard deviation is non-negative. Okay, so that's just one little trick of making sure these constraints hold. Okay. So the nice thing here is you can also make assumption about your prior distribution over your latent variables. And in particular, if you also assume your prior distribution P as a Gaussian, then there is an analytic solution for the KL term between two Gaussians. Okay, so you don't need to remember this equation at all. You can basically find this on Wikipedia. But the point here is previously the first part, right? We have this reconstruction error there. And the second part, by choosing both Q and P as Gaussians, we also have analytic solutions for KL, so that the entire lower bound objective is treatable almost. Okay.
Sorry, another question.
Yes.
How do we, it's the P being Gaussian is just sort of like an assumption.
Yes. Yes. And in fact, in some cases, you might actually prefer not to use Gaussians. But just for the sake of, let's say, the image generation, okay, Gaussians is often the default choice. Okay. Yeah, to ask questions along, right? So I mean, I just said that you have a treatable, objective almost. Okay, there's one thing that is still missing. Okay, which is okay. Now we know these two terms, but how do we actually compute it? In your, let's say, laptop or your GPU cluster. Okay. So let's just have a recap, right? So this is our objective, as we mentioned before. So we already addressed the problem with the KL term. But the first term, even though it is a Gaussian distribution, let's say with L2 error, you can replace that, but you still need to compute the expectation, right, over both the Q distribution and the data distribution. And remember, your P distribution here, right, includes another generator, which basically means if you were to actually explicitly compute this expectation by summing over all possible Z, then you need to pass this Z through this neural network every single time, again, computationally intractable. So we clearly need to find some way to, estimate it in a efficient way, okay? So the important trick here is called Monte Carlo estimation, right? So it is basically a very simple statistics thing, right? If you ever want a expectation of some random variable, you can definitely get samples from that underlying distribution and then get an empirical average of it, right, as the approximation to the expectation you want. So here is exactly what we are doing, right? So we want to compute the expectation of the log p term under my Q distribution. Okay, so I'm going to do this sampling-based approximation, and in particular, people found that you only need one sample, okay, to make it train in practice very well. Okay, so yeah, okay, so I basically said I'm going to get a sample for the Q distribution, which is doable because you have a Gaussian distribution. We will talk about how to do it later, right? So once you get this Z variable, you plug in that through your decoder, pass it only once. Okay, and then evaluate the corresponding Gaussian distribution again. So this basically says, okay, I can compute this term. And in particular, if I want to compute, let's say, the optimization procedure based on variant descent, I can also differentiate through this log likelihood term to get the gradient with respect to theta, which is the decoder parameters. Okay, so this part is quite nice in terms of training the decoder. Now, another question here we have is we also need to train the encoder. Okay, we also need to train the Q distribution here. So, yeah, in order to train the Q distribution, we also need to compute the gradient, right, with respect to the VAE objective. The K-out term part is easy, right? You have analytic solutions, you just differentiate through, right? But with this multi-color estimation, right, of the first term, okay, it is not clear, at least from this expression, how are you going to differentiate this multi-color estimate with respect to phi, which is the encoder parameters. Okay. So the next important thing here is called repenetration trick. Okay, so this is actually quite an important trick that has been proposed in these papers and also been later on used very widely. So the idea is the following. You might want to consider exactly how you compute the samples from the Gaussian distribution, right? So if you have your Q distribution as a Gaussian, then getting a Gaussian sample is just as simple as, okay, you first get a standard normal sample, and then you scale it up with the standard deviation of the Q distribution, and then offset or shift it with the mean of the Q distribution. Okay, so this is what you can do. Now, the interesting thing here is if you actually plug in, let's say, this particular equation for something like Gaussian distribution back to our previous, multi-color estimate. Now you can actually see very explicitly where does the dependency of phi comes from, right? So essentially it tells you that, okay, the latent variable I'm going to condition on is directly dependent on the encoder parameters, so that I can just directly differentiate through, right? Okay, so that the way it works is the following, right? So let's say this L is your objective, right? So you can apply chain rule. First, just think about this T as basically your Z variable. You compute the gradient of your objective here with respect to Z. And now, via this repenetration trick, you know that this Z they also explicitly depend on the parameters phi, and you just differentiate through. Okay, so this is actually in practice how people actually implement the automatic differentiation procedure for the likelihood term here. Okay, so I think we are getting to the end of, let's say, the non-sequential part. Okay, so just to summarize, okay, so let's just combine all the ingredients together, right? So remember, we have two terms in objective. One is basically the likelihood term, where by assuming that you have a Gaussian distribution, then it just goes back to a negation of the reconstruction loss. Okay, and then also by applying this reconstruction trick, right? Then you will see that the input to your decoder will also be directly dependent on your encoder parameters, so that yeah, you really see this autoencoder part, right? So the input is X, you go to encoder and go to the decoder. Okay, the interesting difference here is this is a stochastic autoencoder because you're going to inject noise in the sampling procedure. Okay, the other term is the KL, and as we discussed, if you're going to use Gaussians, then yeah, you have analytic solutions, then you can just directly compute it. Okay. So I hope this static version of latent variable models is clear to you. Okay, maybe I can pause a little bit to see if you have any questions before I go to the sequence part. Okay, cool. So yeah, we can talk about sequence modeling. Okay. So the interesting thing about basically these sequence models are essentially about how are you going to design your P and how are you going to design Q. Okay, it can actually give some very interesting results. Okay. So the first thing we're going to talk about is basically deterministic dynamics. Okay. So here I'm basically visualizing one particular design here. Okay. So this design is basically trying to utilize a recurrent neural network with some random initial states, H0 equals to Z. Okay. So why you would be interested in these kind of models at all? right? So imagine, so this I'm just visualizing you one video of simulated bouncing ball. Okay, so if you assume like there is no friction or whatever other kind of constraint, just purely look at this idealized environment. Then once you know the initial position of the ball and also let's say the initial velocity, right, of the ball, right, then the full trajectory of the ball is determined. Okay, so this is what I meant by deterministic dynamics. It means once you know the initial conditions, the entire trajectory has been determined. But obviously, if you're going to, let's say, generate different kind of, let's say, bouncing ball, videos, right? Then you need to change or shuffle around different initial conditions, and that's basically why we have this latent variable z there, telling you that the initial condition is random. But once I have sampled a initial condition, then I can roll out these dynamics. And this image, right, is actually rendered from a from a very simple simulator. It means that this simulator might be very low dimensional, right? But you need to render it into high dimensional images. So that explains why you also have, let's say, these arrows pointing from your hidden state age to the actual observations. In this case, they are the video frames. Okay, so yeah, so I hope this motivates you why you might be interested in this kind of sequence VAE. Okay, so in this case, usually what people do to parameterize this generative model P is the following, right? So yeah, I'm going to also assume I have a prior over my initial conditions, and then based on my initial conditions, I can generate all the frames. And then in particular, in this case, right, since you only need to know the hidden state at that time to generate images, right, you can also assume, this is factorized over the time step, as long as you know, basically the current hidden state. And you know the current hidden state is fully determined, again, by your initial states via a rollout of a recurrent neural network. Okay, so this is our P model. Okay, so the question comes back again. Okay, we want to learn this model parameters, and we know that maximum likelihood is intractable, so that we can also rely on, let's say, variational inference, right, to construct this lower bound objective. And remember, in the lower bound objective, we need to actually propose a Q distribution. Okay, so now the question here is, what kind of Q distribution are you going to use? Okay, so one method that people often use is basically say, okay, I just take the entire observed video as input, okay, and then I try to do something somehow to just parameterize a distribution over my initial variable z, okay. So how you actually do that is an interesting question, okay. So an example of doing this is something called bidirectional RNN. Okay, so bidirectional basically means, okay, I'm going to define two RNNs. One goes for the, let's say, the forward direction, and another goes for the backward direction. So from this visualization, you can basically see that, okay, the forward direction RNN is basically this path from F1 to Ft. Okay, and then you also take the same sequence as input, but then you just roll it out backwards, right? That gives you this backwards RNN result, BT back to B1. Okay, so that basically means, when you run these two directional of RNNs until the end, right, you will get basically this feature FT that hopefully capture the information of the entire sequence for the forward direction. And similarly, this B1 captures the information about the entire sequence, but in the backward direction. So the final thing to combine is basically, okay, I can take this FT and also B1 as input to another neural network to combine the result. And this neural network will output, let's say, the mean and the variance of the Q distribution on Z. So we are going to use Gaussians. Always you just use neural networks to output its mean and variance. Okay, so this is a quite popular way to parameterize a encoder to basically get this inference here. So let's just have a look at the objective here. Okay, so the objective here is essentially a little bit twist from the previous result, right? So the previous objective we have definitely includes both these data latent term as well as the KL, right? So now we actually include a particular beta coefficient here to somehow balance the learning between the reconstruction and also the paradigm mix. So yeah, it is actually quite important that you set this beta in a very careful way. The reason is the following. So in the previous example, right, for the image case, we only assume P, right, P of Z is a simple Gaussian distribution of mean 0, variance 1. So it basically means you don't need to learn it. But in this particular case, well, okay, let me see. So the PZ here, we can also assume right. So the PZ here, we can also assume this to be a Gaussian distribution of 0 and 1, right? But now you have much longer sequence, okay? Which basically means that it is quite easily that your first term will outweigh the second term, okay? So people often actually try to tune this beta quite carefully, okay? You will see this beta term effect even more in later on models when we go to the stochastic latent variable setup. Okay. Yeah. So in summary, basically the objective is almost the same as the previous image case. The only difference here is now you're in a sequence setup, right? Your observation is basically a sequence, so that your encoder also need to take this sequence into account and build a recurrent neural network or other kind of sequence-based neural networks to get the entire sequence information to infer your initial conditions. Okay. So there is another potential architecture that you might consider, okay, that is still, again, deterministic dynamics, but in a slightly different way. Okay, so this is the architecture that has been used in some setup that people try to build a video generator that describes some sort of, say, environment. So you can basically think about, let's say, this Z, instead of only specifying the initial condition of the dynamics, just think about it as sort of like the environment information, okay, of the simulated environment, right? So, I mean, this is basically a robot pushing kind of video sequence recorded by some research scientists at Google. You can imagine that, say, this that somehow describes, basically the scene information as well as maybe the, the physical parameters of that particular robot arm. Okay, so this kind of, parameters definitely impact on the entire sequence, every single step. Okay, so that you can basically see why we put this connection from this environment variable Z to every single part of your recurrent neural network. Okay, so basically, I mean, the equation for variation inference is still the same. It is still basically the same equation here, but essentially how you compute all these distributions will become different depending on your architecture for the P model and the Q model. Okay. So I guess so. This is two examples. These are two examples for this sequential latent variables with deterministic dynamics. And you can see that although we have a sequence here, we only have one latent variable Z to infer, which makes this case still quite similar to the previous image case. But things are going to get a little bit more complicated. Okay, when we talk about stochastic dynamics. Okay, stochastic dynamics, the idea is the following. Basically, it says that even the current latent variable zt, the future trajectory of the zt can still be stochastic. One particular example that can be quite easy to understand is basically, let's say you're going to simulate some kind of, say, autonomous driving kind of, say, this car path sequence, right? You clearly see that here, right? It given the position of the car here, it is clearly you have two choices, right? It is not like, oh, you have the car position here. It's fully determined that you're going to go straight or going to turn. There are actually basically a lot of choices. And let's say if the car keep on going, right? It is possible basically at some point they decide to, let's say, turn left, right? So again, this basically says if you have a some kind of, say, sequential data setup where knowing the current states does not fully tell you where the future states will go, then you need to use stochastic dynamic models. Okay, so yeah. Okay, in particular, a very widely used stochastic dynamic model in, let's say, in the control literature as well as in machine learning is called linear Gaussian state space models. Okay, so the idea is the following, right? So we have this model where the dynamics in the latent space that is basically linear, right? Because it just tells you that the current state of that is basically a linear transformation of the previous states plus a noise. Okay. And similarly, the emission process where you transform the latent states that to the observation x, they are also linear, right? So x is basically a linear function of z plus also a Gaussian noise. Okay. So yeah, so this basically builds a state-based model that gives you a joint distribution of x1 to t and z1 to t, factorized in this way. I think this can be seen also from the visualization of the graphical model here. Okay, so there are actually quite a lot of different variants for this, right? So first thing is you can consider whether this model should be stationary or not. Stationarity basically says your dynamic behavior at any time step are all the same, right? So if you're going to assume stationarity, then it basically tells you that these A, B, well, these matrices, they are all like constant through time. Okay, so yeah. And the other thing that we can do here is, okay, we also need to learn these matrices, right? These ARCQ matrices. Okay, so I hope at this point it is quite familiar with you that we are going to do maximum likelihood. Okay, but the interesting thing here is, okay, maximum likelihood, right, requires you to integrate out these unseen latent variables Z1 to ZT. But the nice thing here is because they are all Gaussians, and we know how to marginalize Gaussian variables, then in this case, you do have solutions. But we are not going to, let's say, just construct a big giant Gaussian and then marginalize all the variables. And instead, we will actually use this chain structure of this dynamics and do this online marginalization, which is also called filtering. Okay.
What is the relation of this genesis and the Kalman filter?
Yeah, this is actually the underlying graphical model of Kalman filter. Okay. And yeah, so that's basically why I said this is actually a model that is often used in control literature as well. But we machine learning people are interested in this model because we are going to also extend this thing to nonlinear cases later. Okay. So yeah, but let me just explain to you this idea of filtering. Okay. So I mean, our goal, right, is to marginalize all these latent variables. Okay. To get to the marginal distribution of P of x1 to t so that we can train this with maximum likelihood. Okay. So yeah, we need to integrate out Z1 to t, and then we plug in the factorization so that it tells us we can do this. Now we can actually select the ordering from Z1 to ZT and iteratively integrate out these things. And we will have some nice indications. Okay. So as I said, right, the first step is I basically just separate out Z1, okay, and then group all the other things together, right? So this means I can at first integrate out Z1 and then integrate out the rest of the thing, okay, right? So this gives me some integration result that depends on Z2, okay? Now the second step is, okay, now I can again separate out Z2 and then leave the rest of it, right? And then I integrate out all the terms that relates to Z2. Okay, so this again, right? Given that previously I already have the first integration result, alpha 2, right? I can also basically just calculate it out. The nice thing about it is all these results are basically like Gaussian-ish, so that there are analytic solutions for this. Okay, so yeah, so I've got this Z3, right? So I think you know the rest of the story, right? The rest of the story is basically I just keep on basically separating out these variables. Okay, I integrate out these Gaussians. Okay, so there are some nice things here, right? So as we discussed, right? So what you need to do is basically you iteratively integrate out these latent variables, and this is something also quite similar to message passing, right? So you can basically think, let's say that the last round's integration result as the previous forward, as the current forward message, okay? And then I incorporate in the future transition, which is the current time steps, right? And also the current observation. I just integrate out basically that t, right? This will give me the new forward message to the next time step. Okay, so this is the iterative algorithm. Okay, so there's an interesting result to tell you what exactly is these alpha t messages. In particular, these alpha t messages are actually the joint distribution for your x up to the current time step t, as well as your next time steps little variable z t plus 1. Okay, so don't worry how we actually get to this, but this is just a matter of fact. Okay, so this basically says, okay, so let's think about basically the last step, right? So we keep on passing this message until the very end when we hit sort of like the last time step t. Okay, which means I've got, let's say, this alpha t here as this thing, right? I plug in the last observation and then I integrate out the last latent variable. So this will give me back the marginal likelihood we want for maximum likelihood. In other words, in this latent Gaussian SSM setup with this filtering, well, it is actually also called Kalman filtering, right? You can actually compute this marginalization in linear time, rather than say, oh, I explicitly construct that super big giant Gaussian and then marginalize out all the latent variables. Okay, so this is quite nice. But the other very nice thing here is, okay, if you are interested in also trying to infer the latent states, okay, given a particular sort of like observation sequence, what would be the corresponding latent states that have generated this particular sequence, right? So this is called inference problem. You can also solve this problem with Kalman smoothing, okay? Anyway, so yeah, the online inference is the following, right? So as I said, right, we want to infer the latent variables given the observations. So one strategy you can do is to do this filtering inference. So given, let's say, the sequence observation up to the current time step small t, what is the filtering posterior for my latest latent variable zt? Okay. So yeah, so this is quite straightforward. Okay, so just recall our previous statement that this alpha message, right, up to time t is basically this joint distribution. Okay, and then what you can do here is to basically play around with Bayes rule. Okay, you don't need to understand too much about how you can play around with this, but Bayes rule tells you that the posterior that you are interested in is essentially proportional to basically your current message multiplied by your likelihood coming from, let's say, contributions of the current time step. Okay, so this is, have a Gaussian structure. This is also Gaussian. So if you have Gaussian prior, Gaussian likelihood, then the posterior is also Gaussian. So there are basically analytic solutions for this. Okay, so this is just probably the take-home message for this particular procedure, right? The filtering posterior is essentially proportional to the current likelihood times the current forward message. Okay, so this is one side, but there is another question that we can ask, which is called offline inference, right? So instead of trying to infer, let's say, the state zt for using the observations up to the current time step, I can say, okay, I give you the entire trajectory. I want to ask what would be the latent variable of some intermediate states look like. So you can notice there is a difference here, which is the big T rather than small t. Okay. So it means that somehow you need to look into the future. Okay. So how do we actually look into the future, right? So there is this interesting thing. Yeah. Okay. So let's just go back to the forward pass, the filtering one, right? So this is our current message, right? And again, I just use base rule again to construct how you're going to get this moving posterior. And the interesting thing here is you can see that now this is dependent on the current as well as all the future observations. Okay, not only the current one, but also all the futures. So we need to find some way to actually compute this term in order to get our smoothing posterior. So yeah, so the idea is, again, you can do things like what we are doing in of integration, right? And also do things in backwards. So to see this, right, the first thing to notice here is all the future time step observations, they also depend on the future latent variables, right? So you need to marginalize all the future latent variables. Okay, so we can do the similar trick again. Okay, remember previously we do this kind of say sequential marginalization, but now we are going to do these things backwards. Okay, so here's what we're going to do. Okay, we need to integrate over zt plus 1 to t. I'm going to first separate out the last variable. Okay, so the last variable is something that looks like this, and I assume, let's say, the first backward message is only 1, so basically this time it does not exist. Okay, so I can definitely for sure first integrate out that big T. So this gives me, let's say, some result depending on the previous time step zt minus 1. I repeat the same thing again. Okay, I'm going to separate out, let's say, that big T minus 1 and all the others. And I'm going to do the integration over zt minus 1. Okay, so, and then similarly, you get another message. Okay, so you can basically see the same logic, right? You just repeat this process and then integrate backwards. So now the interesting is the following, right? So if you're going to, let's say, do this integration, right? So you also, again, have this recursion expression, right? Where if you're going to compute the new backward message, right, then you're going to just get the current backward message, okay? And then also taking the current transition as well as the current observation in. And then these three terms, they are all Gaussian forms. So we can still compute the integration in an analytic form, okay? Yeah, so this is also a matter of fact. So don't worry if you if you don't see it, but this is just also another fact, okay? So now the interesting thing here is that you can see we now can combine both the forward message and the backward message. Remember in the previous result here, right? So we have this posterior that definitely contains the forward message that we have already computed, okay? Now, in our derivation, right, we also tell you that you can compute the backward message. And the backward message will basically give you basically the distribution of the current latent variable and also all the future observations, right? So you then just follow the previous base rule that you combine the forward message up to the current time, and also the backward message also up to the current time, and then also add in the final observation. So this will basically give you the smoothing posterior. That's what is the latent state of some time given the entire trajectory. Okay, well, yeah, so this is, I think probably this is one of the most important results in control theory, okay? But it has also been quite inspirational for development in, you know, sequential latent variables. But let's just show you how it works in a toy example, okay? So yeah, so this is basically a simulation from a ground truth linear Gaussian SSM, okay? It tells you that, okay, the observation in these green circles are sort of like noisy perturbations of the actual ground truth trajectory in blue, and the blue one is actually the z variables. Okay, you can think about it as sort of like the noisy observation of a ground truth trajectory. Now, given that you only observe, let's say, these green circles, can you infer what exactly is the underlying trajectory, right? So what you can do is, okay, so I can try to infer, let's say, the latent variables, right, using the information up to that particular time step. So this gives you the filtering result. Okay, well, the black circles are basically the uncertainty estimate around your estimation for Z locations. But essentially, it gives you something looks okay, but not perfect. Okay, so filtering can give you something like this. But if you can actually also include the future information to infer basically where the current latent state should be, right? You can basically see that it gets much more accurate. Okay, comparing to like the filtering estimate. So this essentially tells us again, right, that in this stochastic dynamic model, in order to infer the latent state, right, you rather want to use both the history as well as the future information, okay, to basically infer your latent state. And this also gives some interesting design choices for the nonlinear version of this, which we will discuss now. Okay. Yeah, okay. So previously we talked about linear dynamics where we have very nice solutions, but apparently for real world sequences you want to do nonlinear stuff. Okay, so this tells you, okay, instead of using linear functions for zt, zt minus 1, I'm going to use nonlinear functions. Okay, so you can still assume these are Gaussian distributions, but it is no longer linear Gaussian because the transition function as well as the emission function f and g, they are no longer linear. So it means that our previous nice solution, okay, we still need to do this parameter learning by maximal likelihood. Again, we need to marginalize out these latent variables. But now, because you have nonlinear transitions, right? The joint distribution is no longer linear Gaussian. Okay, so that you cannot easily marginalize out, let's say, these variables in a sequential way as we previously described. Okay, you cannot do it. So instead, people have definitely tried a lot of ideas. In the control literature, I mean, people have invented a lot of these, different versions of common filtering and smoothing, right? Like the extended common filtering, which basically say I'm going to linearize this model, or some other models, or some other methods like unscented common filtering and smoothing. But in the machine learning literature, we are going to do, what people do with VAEs. Okay, we're going to do VAEs. Okay, so this basically says, okay, I won't compute these integrals to get approximate NRE. Instead, I'm going to get a lower bound. Okay, as we have done before. So now you have to talk about some choices. Okay, about how you're going to define this Q distribution, because now your Q distribution includes these variables, right, from Z1 to Zt. Okay, instead of only inferring, let's say, the initial condition or the global environment variable. Okay, so the first choice here is, okay, you can think about it as a filtering encoder, which says, okay, maybe I just need the observation up to current time in order to infer, let's say, the sequences here, okay? So one way to do that is, well, you just use a single RNN, right? So imagine that you're going to have a forward RNN, right? So each time step, your RNN is going to take, let's say, the current observation as input and then combine with the previous recurrent state. And this will basically update the recurrent state of this Q network and also output, let's say, the mean and the variance of, let's say, your current latent variable. Okay. So yeah, this is one typical strategy of parameterizing the Q distribution with this filtering strategy. Okay, so now this tells you, right, that okay, we just plug in the elbow here. The first line is just plug in the equations, and then just to keep you remind you that now we have this P and Q taking all the latent variables that went to T as input. According to this structure, right, you can basically see that as long as you know all these kind of, say, the RN states F1 to Ft, right, these latent variables are independent. So it tells you that, okay, the first expectation term, right, can also be factorized into this case, because you also assume a factorized P distribution. Okay, and this one is actually quite similar to the previous example of filtering posterior, where you only trying to guess the current state given the structure you have seen so far. Okay, but from the previous example, right, we can see that we want some kind of future information to also help, right? So again, this tells you you might want to use bidirectional RNN, right? So previously in the deterministic dynamic case, we also tried the bidirectional RNN. So now here's how it works, right? So again, we run two RNNs, right? One RNN is F1 to FT for the forward direction, and another RNN is BT to B1 for the backward direction. So now instead of only using information at FT and also B1, you need to actually now think about how to combine basically, AFT and BT at every single T time step. Okay, use a neural network to combine these two RNN states at each time step to output the mean and the variance of the Q distribution. Okay, so this somehow you can use the future information. And if you're going to write down what exactly it looks like, because in this case, we still assume you have a factorized distribution over Z, right? And using the previous logic, you still see now the objective function, at least for this expectation of the likelihood, factorized into this case, where it's basically simulating a smoothing posterior. Okay, I guess I'm running out of time, but let's just very quickly see some examples of this. Okay, so one of the state-of-the-art model that actually use this idea of nonlinear SSM is this thing called recurrent SSM, and their latest version, if you want to search, is actually called Dreamer V3. I mean, they have V1, V2, V3. They are also basically based on this similar architecture, where you can see that it is a stochastic dynamic model where you have stochastic states, and it is a reinforcement learning sector, so that you observe both the observations, which are the videos, as well as the reward. And it is also conditional on actions, because this is a reinforcement learning problem. But essentially, what they did is they used this recurrent SSM as the model, and then train this model on basically this reinforcement learning play of these different environments. Okay, and then they can test time conduct model-based reinforcement learning, which basically means you need to simulate the potential future using your model. Okay, which is really tests how good your model is in terms of generating, let's say, the future. At least I think this is the state of the art within this SSM in the domain of model-based RL. So that if you're interested, you should definitely look it out. There are some other applications as well that some time ago, DeepMind, they are also interested in sports analysis, right? So they've previously done this football player trajectory analysis, where they want to understand how different players interact with each other, so that they actually build a recurrent neural network based generator, but they are also embedded in some interesting architecture like graph neural networks to explicitly model the interactions between the players. So yeah, they actually train these things in the way as I described. This is a variational RNN that is quite similar to the state-based model I described, and at least they've got some very interesting qualitative results. Okay, in terms of the visualization, and I think their forecasting result is decently okay. Okay, I'm going to wrap up. So yeah, so as my group is doing this sequence data, right? So, but the reason why we are interested in this is, sequence data generation is far from being solved. So today I only talk about very basic stuff. Okay, probably not very sort of like close to the papers reported in the state of the art, but there are some interesting recent trends, right? I mean, transformers are everywhere right now. Okay. In terms of predictions. But in this domain of modeling dynamics, there is this interesting trend of basically trying to propose a underlying the model that the underlying model is actually continuous time, but they have very efficient discrete time computation or approximation methods, so that they can actually be executed in both continuous time and discrete time. Okay, so there are some interesting references here if you are interested in looking at that. So my group also work on something related to this, which is we call causal representation learning. In that, we are interested in not only being able to predict or forecast the future in a very good way, but we are also interested in making sure that the learned underlying dynamics is the ground truth dynamics. Okay, so yeah, so there are some very interesting work there. Okay. Yeah, so yeah, thanks very much. So I'd like to thank my lab members of doing this. And if you're interested in this topic and also basically in generative models in general, so there is this European generative modeling summer school that they are now accepting applications. So I'm going to also speak there. So I think this is actually quite nice for a first year or second year PhD student to go if you are interested in various kind of generative models, not only like sequence, but also, let's say, diffusion models, energy-based models, normal Hanging flow, or something like that.
So can you go back to the football problem?
Oh, yeah?
So I would modify the problem such that, let's say that I'm able to measure the position of each player, but I'm not able to anymore identify the players. So they are all basically look the same. And then I get the time series, basically a video, let's say every second or something, the game. And then I would, based on this measurement, based on this data, I would need to reconstruct the trajectories of players. But I can't identify the players, so they're not cannot label them.
Oh, yeah?
So how would it work? Like, because you discuss this mostly, I can see how it happens for one single player, but then I get this like problem of like associating and then the combinatorics.
Yes. So, the use of graph neural network here, it essentially depends on the case that you can actually identify each of the players. Right, you need to actually know, let's say the blue player at this time step is, let's say, at this location, which means their input data is actually, let's say, the position and maybe the velocity of each of the players, so that you can actually build a graph. So if you don't have that information, I mean, okay, so probably the one of the very difficult case, which possibly can be done, is you only have video recordings, okay, of let's say this gameplay. Maybe this top-down view you may have, but you don't actually know, that blue player is a player of whom, right? So in that case, one way to do that is just view this as a video sequence. Okay, and then you try to actually generate this video sequence. So it can work if you have a very powerful model and also enough data, but it's not efficient because you are going to spend quite a lot of time generating, let's say, this background information that might not be very useful. A better strategy is from that video sequence, you actually want to assume there are some sort of like underlying objects within that video sequence, and then treat that object as latent variable. You want to infer from that. So there are this entire world of research called object-centric learning. Object-centric learning is essentially, as I described, that you only have video rendering of a scene, or let's say this top-down video of a gameplay. You actually want to detect the object within that particular video sequence, and then try to understand the interaction behavior between objects you detected from the video sequence. So that is an entire different, well, very interesting research direction.
So you're basically saying that because I just wondering how so you mentioned graphs, so you need some like representation to solve the problem. The state space model itself cannot like solve this my issue of, let's say that, let's think about like it's a box full of particles, and the only thing what you can measure about these particles is their position. They don't have any other quantum numbers or labels. So, and I take a video, but it's sparse enough that they like move far away from their previous position. So the problem becomes like non-trivial to track them all of them.
Yeah.
So
I think they're high frequency track.
yeah, but then it's like if I start from some like random position and then like if the measurement is sparse enough, because otherwise the problem is too trivial. It is like if you have some high frequency sample. So I don't want to solve that problem because then you then you can just like look at the smallest like difference between the frames or something.
I guess it depends how far you're trying to predict in advance, but you might have high frequency data. I guess they're interested in like, you know, predicting like a minute in advance or something like that, like for, but they're allowed to have high
Well,
frequency.
they cannot do 1 minute. Okay, so
Some sort of something that is long compared to the frame rate of the videos, but still a regular video frame rate. I guess I had a kind of maybe a different kind of question, which was so you mentioned how you had to kind of introduce this bunch factor beta when you were considering the deterministic case. And I was trying to think about like, why would you ever not just want to assume that you have some kind of stochastic case? So you could, so even if I believed that I had some deterministic dynamics,
yes,
you might think that, you know, because of sort of just error in your observation noise, you kind of have to stick a big beta factor in to try and make yourself particularly, you know, committed to your initial condition. Whereas even if you believe you did have the deterministic dynamics, you might want to use this Kalman filter formulation anyway, because it sort of makes you more robust. Is that how it's
okay, so I think that's an interesting thing here, right? So, I mean, I said, right, in terms of deciding which dynamics you want to use, you might want to think about the underlying problem. But indeed, there are cases that maybe the underlying dynamics is deterministic, but you actually want to use the stochastic model. It's exactly as you said, you might have a very high measurement error, or you might want to avoid, let's say, this, discretization error. If let's say your underlying dynamics is continuous, but you only measure like in a very say spaced out way. So people do consider, you know, using stochastic dynamics in the case where the underlying dynamics is actually deterministic. Okay, so but I guess that's not related to this beta factor that we are talking about. I think this beta factor, right, is purely people observe that. Okay, let me see. Okay, so it's basically the fact that people observe that you cannot simultaneously maximize the first term while also getting this second KL term very small, because there is a trade-off, right? So so that people found that this trade-off can be very tricky to control, so they introduce this beta term in general. And I mean, this beta term, people also use it in even static case, like, you know, using a variational autoencoder to generate images. So this is this one. But I guess another thing that I can mention here is this beta factor gets even more important in the stochastic case. So the reason is, let me see, where is this slide? Okay, wait a moment. Yes, okay, so the reason is the following. So in test time, you want to roll out your prior model, right, to do the forecasting. Now, if you look at this particular equation, right, the only way that you're going to learn your prior dynamic model, which is your P model, is via this KL term. So it means that if you, let's say, you don't set this beta term to be quite significant to encourage you to minimize this KL, then your prior has no chance to actually learn what is the underlying dynamics. So yeah, so this beta term becomes even more important when you do stochastic, you know, latent variable models.